I think you can start.
Wonderful. So today we're talking about Riemannian. Yes, thank you. Today we're going to be talking about Riemannian metrics. And you'll see what those three shapes are about here in a moment. Just as a reminder, for this seminar, I'll be referencing Chapter 3 of Riemannian Manifolds, An Introduction to Curvature, by Mr. John Lee. So that said, let's begin with the question that everyone asks these academics. Who asked? So we have these classical geometric notions such as length, angle, curvature, and volume. And those are great, but we also have our classical topological notions such as diffeomorphisms and covering spaces. The trouble is that these are often two separate things, like topology is inherently squishy and stretchy, and so things like length and angles go out the window. The beauty of the Riemannian metric is that we get Riemannian manifolds, which is kind of a happy marriage of these two notions. And so now we can talk about things like volumes of manifolds and such. So let's begin. A Riemannian metric is roughly 5.5 feet. This is the average height of a 19th century German man. Although, okay, sorry, jokes aside, what actually is a Riemannian metric? A Riemannian metric on a smooth manifold is a two tensor field G that is symmetric and positive definite. And just as a reminder, a two tensor field is a smooth section of this happy little tensor bundle over here that Ashwin and Jacob were talking about last time we were here. And symmetric, of course, meaning doesn't matter which order you put the inputs in, we get the same thing. Positive definite, you plug in a vector with itself, it's greater than 0 unless the thing you're plugging in is 0. So that's great from an abstract thing, but something that's a bit more helpful is to think of a Riemannian metric as an assignment of an inner product to every single tangent space. So for every point, you get an inner product. In fact, you already know an example, the inner product we all know and love. The dot product happens to be an example of a Riemannian metric, in the case of the manifold being Rn. So just as a quick warning before you proceed, I know I keep saying the word metric, although it's not really a metric in the usual sense of the word, although there is some sort of overlap. So questions about the definition before we move on to Riemannian manifolds? Sweet. So if you put together a Riemannian metric and a manifold, you get what's known as a Riemannian manifold, usually denoted by the pair Mg. M denoting your manifold, G denoting your metric. And so if we make a distinction, of course, we want to make sure that this distinction is actually a helpful distinction. So you might wonder, if Riemann is the one who coined the term manifold, does that make all manifolds Riemannian? As it turns out, all manifolds do actually admit a Riemannian metric, although it's not because Riemann named them. So here's our first happy result. Every manifold admits a Riemannian metric. Since we have quite a bit of ground to cover today, I'm not going to go into the fine details of this proof, but there's something you can certainly work out in the comfort of your own basement. But the idea here is that we know that manifolds are locally Rn, and as we mentioned earlier, there is a nice inner product in Rn. Rn has the dot product. So we know at least up close manifolds can have like these nice little inner products working for them. So only things we might wonder is maybe where the open neighborhoods on the manifold kind of overlap. And so what do we do if we have a local property we want to extend to the whole manifold? We take partitions of unity. So great, so now we have this nice way to assign metrics to any manifold you can dream of. Are there questions before we proceed to the next topic? Sweet. So now let's talk about those geometric notions that I promised you. So if you recall from your multivariable calculus class, the dot product in Rn allows us to define the length of vectors by dotting the vector with itself and then taking the square root of whatever pops out there. Yes.
So about the slide.
Oh, yes.
How about the uniqueness?
Oh, the uniqueness of the metric? Is that what you're asking? These metrics need not be unique. Manifolds can admit multiple different Riemannian metrics.
Thank you.
Yeah, no problem. Great question. Yes. So we have these lengths, and also we can define angles using our dot product. And so it seems reasonable that we can extend these notions to Riemannian manifolds because Riemannian metrics generalize the dot product. So we just do this in the same thing. So if we want to talk about a vector in some tangent space, we can define the length of that vector to be what happens whenever you take the inner product of that vector with itself, and then the square root of that. By the way, to avoid things getting cluttered, I'm going to be using this Langle-Wrangle notation instead of just using GEP of the vectors we're putting in. This is something that Lee does as well in the text. Likewise, we can define the angle between vectors to be the unique value of theta between 0 pi, satisfying the equation cosine of theta is equal to the inner product of x and y divided by the length of x times the length of y. And now that we have a notion of length and angle, we can now talk about things that are related to these. So just like in the usual Rn case, two vectors are orthogonal if the angle between them is pi over 2, and a collection of vectors is orthonormal if their lengths are all 1, and if they are pairwise orthogonal, just as in the Rn case. But as a great commercial guy once said, but wait, there's more. We also get the other geometric notion that we love to see by first considering, okay, so what is length really in terms of vectors? We can take the length of vectors and add them up end to end, and that gives us a notion of length. If we take orthogonal vectors and consider like the space between them, and then add up all those squares, those gives us area, and we can do a similar trick for volume. So it seems to be the case that if we have an orthonormal basis, we can now have a nice notion of volume on whatever manifolds we want. And this turns out to be the case. Riemannian metrics allow us to generalize the notion of volume to manifolds. So here we have this nice result. This is lemma 3.2 in Lee, that on any oriented Riemannian n-manifold, there is a unique n-form dV such that for the basis, for your tangent space anyways, E1 through n, we get that the n-form evaluated at these basis vectors is 1. The only criterion is that these be that this basis be oriented. Otherwise, volume doesn't make any sense, and they need to be orthonormal. Oh, look, I wrote basis twice. Okay. And specifically, if you have a oriented local frame EI and its dual coframe phi, you can actually write dV explicitly as this expression here. You might notice I have determinant of Gij. What is that about? The idea is that we have these little components. Gij is just what happens when you take the inner product of EI and EJ, and those kind of become entries into a matrix. We'll talk more about what that matrix is like later on, but that's that's the matrix we're talking about here inside this square root thing. Excuse me. Questions?
So do you do orthonormal or not orthonormal?
For the
Basis.
basis, yes, they do need to be orthonormal.
So there's no GIJ.
It's just identity matrix.
Yeah, in this case, it will just be the Kronecker delta.
But you're saying in general when it's not orthonormal?
Is this thing for general working frame is fine?
Oh yeah, I guess what happened was that as I was writing this down, I had confused two thoughts together. So in this specific circumstance, GIJ will just be Kronecker delta, so it would just be like, you know, ones along the diagonal and 0 elsewhere. I was just saying that that sort of matrix where we have these sort of things in here does come up more often in more general context, even when the EIJ is not orthonormal. So this is the result of me having two different thoughts at the same time and writing them down without making the distinction. My apologies for the confusion. Yes.
Yeah. So sorry, you're like pretty much spot on here. But like,
Thank you.
It's pretty common not to have an orthonormal frame. Like,
Oh, is that okay?
well, so like if you're working in coordinates, right?
Sure.
A coordinate frame like Ashman and Jacob were talking about, del xi's, right? Those are typically not orthonormal frames, right? So it's super possible for GIJ not to be delta IJ.
Oh, okay. Thank you. So I can just put here like this kind of.
Well, so this property that dv is 1
Mm-hmm.
is something that's special to oriented and orthonormal.
Oh, I see. So like in the more general case that I'm describing down here, this form
Yeah,
here,
this coordinate expression you have holds for any local frame, not just orthonormal.
Gotcha. So more generally,
So the
EI need
It
not
evaluates the root determinant.
be orthonormal. Oh yeah, in that case, yeah. Otherwise, the determinant would just be 1, and then that would be irrelevant. Okay, great. That makes more sense.
Why is the thing in the root positive to begin with is also something what you mentioned? Why can you take a positive spread?
Because actually, I haven't thought about that, but my go-to guess would be the fact that the Riemannian metric is positive definite. And symmetric, yes. Positive and symmetric. Anyway, part of the advantage of having a notion of volume for manifolds is that no more do you have to restrict yourself to only integrating differential forms. Now you can actually integrate functions on manifolds, which makes the physicists very happy. So, yes, that marks the end of this section, and lots of constructive and helpful comments. Are there any more before we proceed to more that we can do with these?
How does that allow you to integrate functions?
Yes, so the way that you can do this here is that it's kind of like this thing from Calc 3 where instead of having to have an... How can I articulate this in a way that makes sense? I guess the idea is that you can like define your integral so that it works for functions, I guess, that there's... yes, I'm kind of floundering at this one.
Yeah, no, you're doing good. So dv is an n form,
Yes.
right? You multiply that by a smooth function. It's still an n form, or an n form field or whatever. And you can integrate n form fields over n chains.
Okay, yes. So the idea, so like multiplying these things kind of keeps it in n form. So
Yeah.
yeah, and this would be kind of like equivalent to.
Canonical n form to integrate against.
I see.
I mean, so like dv is kind of like your like it's only a Borel measure or whatever, but like it's kind of your standard volume form on the manifold. Just like dv is your standard volume form on Rn.
Yes. Whereas like for differential forms, that we could have like different things we kind of choose we're integrating against. I mean, sure, they all turn out the same, but it need not be like a standard form.
Yeah.
Is...
You can only integrate like a k form field over a k chain in your manifold or whatever.
Gotcha. So does that answer your question? Righteous. Okay, so now that we talked about those geometric notions, let's talk about some of our topological notions. So one thing that we might are interested in topologically is when are two spaces the same? And so if we have two things working here, a manifold and a metric, we need to first make sure that the manifolds are quote-unquote the same and that the metrics are the same. So this gets us to the notion of isometry. If you have two Riemannian manifolds and a diffeomorphism between the two manifolds, the diffeomorphism is said to be an isometry if the pullback of this second metric happens to equal that first metric that we got there. That seems like a fair and intuitive definition. And as I mentioned earlier in response to Keigo's question, is that a Riemannian manifold may admit multiple metrics, and so it's worth considering which of these are the same up to isometry. And so, or I mean, if we have different classes of these to begin with. So we begin with a couple observations. Well, since the composition of diffeomorphisms is itself a diffeomorphism, and you can check that if the pullback metric works here, so will the pullback of the, when you do these in succession, diffeomorphisms are invertible, so that means that the inverse function is also going to be an isometry. The identity map is clearly an isometry, and category theory tells us that function composition is associative because we'd like it to be. And if you got closure, identity, inverses, and associativity, you got yourself a group. Which is awesome. Usually this is denoted script I with an M next to it. This is just the group of isometries on M.
Yeah, that's what I said.
Sorry?
Math cal I looks an awful lot like a J.
Isn't that Michelle?
Yeah.
It might be math cal J. The trouble is, I don't like the cursive I because it looks so much like a J. Like, we'll do that, but then it looks like an L.
You could just throw like a school. Yeah, that's
Yeah,
hard.
that's
You know what? I'll do one better. I'll do one better.
It's the best.
So, great. Now that we've talked about when things are the same, we'll do the other thing that topologists like to do. When does one thing live inside of another thing? In other words, how about those subspaces? One thing that's really nice that we can do is that we can restrict the metric on our manifold down to a metric on a submanifold. So if you take your inclusion map from your submanifold to your manifold, then do the pullback on the metric there, you get what's called the induced metric on the submanifold. You want to pay attention to this one. It's a surprise tool that'll help us later, particularly when we start talking about metrics on spheres, because you know the n sphere lives in Rn plus 1, and so that gives us a convenient way to talk about metrics on spheres. More generally, one thing we can do is that you can actually do this thing with any open subset of your manifold. This is what's called a local parameterization, where again you just take an embedding of your open subset into the manifold and then take the pullback of the metric. And again, that is something that will be useful to us as we start constructing some of these metrics later on. In fact, most of the things in these sections are how we can build metrics, because as you might imagine with some manifolds, it's not entirely obvious how we can do that. So if we have a way to construct it from other ones that we understand better, that would be fantastic. And now, what would topology be without products and covers?
Sorry, Mary.
Oh,
can
yes,
you
absolutely.
Use just an embedding will do, but then above it just needed to be an inversion. Which
Yeah, the induced metric is you don't have to do
Yeah, the case up here is that M happens to be a regular submanifold of M tilde, and so that's why we only need an immersion there.
okay.
Whereas U is just any open subset of
Oh,
M.
thank you.
Sure thing. Are there other questions? Okay, so a natural way to combine two manifolds together is to take their product. And so the only thing left to figure out is what does it mean to take a product of their metrics? Well, a natural way to combine linear maps is just to do component-wise sums, and so that's precisely what we do here. We define their product metric to be this thing down here. If you have these two vectors living in your first manifold and these two other vectors living in your second manifold, you can just break up the product metric to just be component-wise products and then add the result there, and that'll give you a metric on your product manifold. So that turns out to be what you'd expect it to be, and then for covering spaces, we also get kind of what you would expect to happen if you have a smooth covering projection, and you have a metric on something down here in the basement, then you can get a metric on the thing living upstairs by, again, taking the pullback of the covering map. Do I have something backwards?
You're talking about same dimension.
Sorry?
You need to be same dimension.
Yes, that's right. We do need the same dimension.
Because it's covering.
That's an important thing. Let's see. Yeah, and this metric is creatively called the covering metric. And as it turns out, there is actually a way to go backwards with this, because we have ways to get the metric from down here to the one upstairs. And there's a sense in which you can do that, but you require some more conditions. So let's say you have a metric on the upstairs that is invariant under all deck transformations. In that case, then there exists a unique metric, G on M, such that G tilde is equal to the pullback of pi applied to G. So if we have the extra condition that the metric upstairs is very under deck transformations, then we also can push it downwards. Yes?
Can I mention like the most boring example of this?
I would love boring examples.
Yeah, so like kind of the most boring example of this is if you want to think like R2 and a quotient by a lattice or whatever. Right, you get a torus out of that, and if you think of any metric you can define on R2 that's invariant under these translations, then this is saying that you can push the metric down to the quotient, to a metric on the torus.
Absolutely, and for that reason, I'm actually a little annoyed that you called it boring, because that's precisely the example I was getting to next. Man, I was so happy with this. But no, yeah, absolutely. Like, and this is to say that you could also get a metric on the 2 torus in a myriad of ways. Like, you could think of the torus as sitting inside 3 space. In that case, you can get your induced metric there. Or you can think of T2 as S1 times S1. And so in that case, you could put your product metric on that. Provided, of course, you already have a metric on S1. And then, as you were just mentioning, we could also do the covering metric here. And as it turns out, all 3 of these happen to be the same metric. Well, this one kind of depends on how you define your metric on S1. Sorry?
The last guy should be flat, shouldn't it?
The last one flat.
The last one's just delta.
Right, yeah, sorry. These 2 are the same. This one is the odd one out. There we go.
So how do you roll this piece of paper around and down into R3? There's no way to do it. The first 2 are definitely not the same.
I'm sorry, what was your... I didn't quite
So
understand.
you have a piece of paper, roll it up and then roll it. You cannot glue them together smoothly. There's no way to do that.
Oh, are they different?
Are they...
First 2.
the first 2 are different? Let's see. I guess what drew me to that is that Lee does give an example of a metric on S1 that when you do take a product, it does kind of give you something that's equivalent to the induced metric here. So I guess it does kind of depend on what your metric on S1 is. Or I may be mistaken in that part of it.
If it's in R3, then you can find a shorter distance than walking along torus. Because there's a torus, then this point and this point. Walk along the torus or just make straight line, then that's different, you know?
Or I guess I'm referring to as the induced metric. So you take the inclusion map of the torus into R3,
Yeah, so
and you can take the pullback metric there.
The
But
shortest geodesic, which on the second model, there's no shortest geodesic. There are a lot of them.
oh,
The exercise you're looking at has it as a submanifold of R4.
As a submanifold of R4. Oh, that might be the difference here.
If that changes anything for Halcyon plane.
Maybe. I will say the part on geodesics is unfamiliar to me, and I'm not prepared to respond to that. But
calculus. If you have this R2 times S1 times I2, you have to glue this end to this end. You cannot do it in space correctly.
Right, you can't do that in R2, but yeah, you can in R3.
You have to glue this end to this end. You have to hold it to glue it.
Right, in R3 that's possible, but
So you cannot do that.
But like you literally would have to stretch.
So, yeah. Like the parameterization in R4, I guess, would be like e to the I theta plus 1/2 e to the I
Oh.
or something.
Right,
So you got two angles in R4, so you can just add your two circles. That's fine.
Gotcha. So I guess maybe like my claim that they're the same is probably not true, but they do all give us ways to put a metric on the two torus.
Yeah. No, that one's tricky. That one got me. So.
I see. But yes, thank you for bringing that to my attention. Any other things before we talk about bringing music into math? All right. My students were recently complaining about throwing the alphabet into math, saying that, oh, math got worse whenever they added the alphabet to it. And then, boy, will they be surprised to find out that we have actually thrown in musical symbols into math. So let's talk about what that's like. So first, if you're chronically online like me, you've probably seen a couple 3 Blue 1 Brown videos. And so one thing you might ask the great heterochromat is, what is his wisdom concerning dot products and duality? Well, what Mr. Grant Sanderson might tell you is that if you take two vectors and dot them together, then you got something like ux vx plus ui vy uz, using the standard coordinates in R3. Then one thing you can do is that you can fix one vector in place and then imagine like varying the other vector. And this kind of gives you a function, so to speak, ux plus ey. So there's the great thing about dot products is it kind of gives us a natural way to convert a vector into a corresponding covector. And so this means that we should probably expect a similar thing for Riemannian metrics. So let me introduce to you the vector flattener. You just toss a vector into flat, and then out pops a covector. And the way that this works here is kind of a generalization of what is going on in this example, only instead of just usual dot product, you just go ahead and use your Riemannian metric here. So you have your components with respect to whatever local coordinates you're using here, and then just leave the second spot blank. And so this is your sort of new map. This is your corresponding covector. And yes, question?
Do we have a vector sharpener, or is it a straightener? What do you call it?
Oh, well, just wait till we get to that.
What are you calling it though? Sharpener, straightener?
I call it the sharpener.
Okay, cool.
But yeah, we call this map x flat because it's obtained by lowering an index. So those of you who have done music would know that the flat is whenever you lower the pitch by a half step. And so that's the same thing happening here. I actually don't know what is meant by index in this context. If someone could clarify for that for me.
Like you write it in local coordinates and you would get just the xi del gamma I thing to be lower by one index of g if you write it.
Oh, okay.
You write g in local coordinates and then you get it.
Right, local. Okay, that makes sense. Gotcha. Thank you for clarifying that. But yeah, and so this is kind of one thing I was mentioning earlier is that we turn what we have into a linear map, and so this suggests that the matrix of the flat map is the coordinate basis precisely. If we do this in the coordinate basis, it's the matrix representing G, which is kind of what I was trying to get at earlier. And that's what I meant by I was having two different thoughts. I was thinking about this thing down here and what I was trying to say earlier. But the point is we can get a matrix representation for G. And if you have a matrix and it's invertible, this suggests that there's an inverse operation to flat. And this is what you might creatively call sharp, where you can toss in your covector, and then out pops a vector. So how the covector sharpener works is, well, to write it component-wise to make it more clear what's going on here, but if you have your covector omega, at the ith component you can obtain by doing this operation here, where Gij corresponds to the ij entry in the inverse matrix of Gi that I was talking about above. Yes?
This is exactly what's meant by like raising an index, right? If you want x, a vector field with a lower index, you take G, right?
Mm-hmm.
Xi, Gji.
Oh, so it's because like the index actually like moves into the upper part of it, not like
Yeah.
That's exactly.
this whole time I was thinking it's sort of numerical thing, but no, it's literally about the placement of the letters on the page. I'm
So that
upset.
That index is up because omega sharp is a vector field. Right?
Yes, it's a.
So it's omega up I del I, right?
Mm-hmm.
And when you flat, it goes from x up I to like x down I. You know.
Oh, and so it's lower down the page. And like you're saying here, we call it sharp because it raises an index up here. See, look, it's upstairs.
You get the same thing when you do a flat, just the other way around. You get Gij, del I,
And then it moves into the downstairs. Yeah. And so, once again, it's worth asking, okay, that's cool and all, who cares? Well, this is where I start to wonder. I wonder if there's a well-known operation that takes a covector and then turns it into some sort of vector field. I just wonder if there's something like that out there. As it turns out, yeah, like the gradient does exactly that. Like you feed it a function, now it pops a vector field, and so now we can generalize the notion of the gradient using the sharp. If you have a smooth map and you take its differential, then just apply sharp to it. This is a way to generalize the notion of the gradient. In fact, this actually allows us to characterize the gradient too in terms of vector fields. It's the unique one satisfying this property here, that you pick your favorite vector, dot it with the gradient, and it's precisely equal to the differential at that value y.
This anything to do with metric?
Anything to do with matrices?
The metric, Riemannian metric.
Oh, Riemannian metrics. I guess mostly in the sense that to define this in the first place, you need a Riemannian metric to do. At least my understanding is that you might need a Riemannian metric in order to develop this thing, because sharp we did because we have this metric, and so that's my very limited understanding about how this might be related to Riemannian metrics. But if someone knows a more sophisticated way that they're related, I am all ears.
Are you also satisfying the relation that you have there?
Oh yeah, exactly. Like this,
The metric.
yeah, this is our just a reminder. Like I'm using the Langle-Wrangle for as like shorthand for G. Sweet. Onward and outwards. Now we get to talk about the piece de résistance of this talk, model spaces. There are certain Riemannian manifolds that are of particular interest, namely Euclidean space, the sphere, and hyperbolic space. And so we'll talk about those individually, what metrics look like on those, and I'm sure we'll see in the coming weeks why these are so special. So first we'll start with Euclidean space. You know it, you love it. But like we said earlier, the natural metric to put on this is just your dot product. And we usually denote this G bar. I think it's interesting to put a bar because the bar is flat and Euclidean space is, for all intents and purposes, flat. Not in the musical sense, as we were talking about before, though. Let's see, but you can be more general than this. Like, let's say maybe you're not working with Rm, but some other vector space. There is a way to convert between the two. And it's kind of like what you expect to happen. You'd pick the metric to be the inner product space on your vector space of choice, choose an orthonormal basis, and that gives you a natural map from Rn to that vector space, provided the vector space, of course, is of the same dimension. Good old Gram-Schmidt processes and such. So that's Euclidean space. Questions about flatland? I know all about flatland. I'm from Kansas. So now we can talk about a more interesting example, the sphere. Quick note on notation, I'll be using SNR to denote the n sphere of radius r. This, of course, lives inside Rn plus 1, so a natural way to define a metric on Sn would be to do the induced metric. You take the inclusion map of Sn into Rn plus 1, take the pullback, Yay. This is what we call the round metric of radius r. I don't know why they don't call it the sphere metric. I mean, it's already there. Anyways. So that's cool. What good is this for? Well, I can show you why maps don't completely suck. It's probably common knowledge that most maps are wrong in the sense that they distort things, and so it's natural to wonder, why do we still bother using maps if they're wrong? And this comes out, before we can talk about why that is, we first need to introduce the notion of what's called conformal. So two metrics on a manifold are said to be conformal if there exists a positive, is ISO positive? Yes, it is. If there's a positive smooth function such that G2 is equal to F times G1. And then now that we have a notion of conformal, we can now talk about things that are conformally equivalent. So if you have two Riemannian manifolds, they are said to be conformally equivalent if there exists a diffeomorphism from M to M tilde such that the pullback phi applied to G tilde is equal to, or sorry, and G are conformal. I might have gotten this backwards. If you spot it, let me know, but I think that's the right order. In the sense of like, does G tilde or G go with phi star? Yeah, it's G tilde, okay. If you are more interested in a visual way to think about it, conformal equivalence is basically, it's angle preserving. Kind of like the notion of conformal you're used to from your complex analysis class. So great, how does that prove that maps are not terrible? Well, as it turns out, Sn is locally conformally equivalent to Rn. Up close, it preserves the angles. So to show this, we only need to prove the following lemma. Stereographic projection is a conformal equivalence between Sn minus the points, we're going to take the North Pole, and Rn. And the thing is, we can kind of pick any point and this will work, so that's how you get that. And so if we have all but this one point being the same in terms of angles to Rn, it would mean that every map you have does still preserve angles. So even though the countries are the wrong size or the wrong shape or whatever, it still preserves you might not know how big Australia is, but you at least know how to get to Australia. Because directions only depend on angles. So great, how do we prove this? So we'll let sigma denote our stereographic projection. I think we have all seen before that this is a diffeomorphism, so I won't go too much into proving that. But since it's a diffeomorphism, we have that sigma inverse is a local parameterization, which remember is an embedding of an open set into our manifold. So we can embed Rn into Sn minus the North Pole. By the way, just some helpful thing that we'll be using later. This is kind of an explicit map for the inverse stereographic projection. Again, I think this is something we've probably all done before as homework, and so I won't go into the details of it, but it's so you can probably work out, again, from the comfort of your own basement. So how does this help us? Well, if we want to show conformal equivalence, we first need to figure out the pullback metric. So if V is your favorite vector living in your favorite tangent space, we can take the pullback metric applied to the round metric. We can take the pullback of the round metric, and then based on how pullbacks and push forwards work, we have a nice way to write this in terms of your usual Euclidean metric. And so that's great and all, but what the heck is this thing on the inside? So we kind of need to take a quick aside and figure out what those things are. So now a cloud of computations ensues. We can write V in like your local coordinates, and you can write sigma inverse of your point in terms of functions xi and tau. And by the multivariable chain rule, you can go ahead and get this thing together. Multivariable chain rule combined with what these things are equal to up here. And then you'll see that this V xi j and V tau happens to equal these monstrous equations. I probably should circle what the final answers are because there's a lot of things here. That corresponds to V xi, and this thing corresponds to V tau. And by the way, if I'm going too fast, let me know, but I don't want to bore you to death with a whole bunch of symbols. Okay, so now that we have those things, we can go plug it in. So again, this is the Euclidean metric here, so you just square each of the components and add them together. Well, yeah, that's what I meant to say. And when you do that and the smoke clears, you end up that G applied to this thing here gives us this. So all in all, the pullback metric here is going to be this thing applied to the Euclidean metric. And this certainly is a positive function, so it does turn out that these two metrics are equivalent, conformally equivalent.
What are the U and V here?
U and V, oh yes, V, first of all, is we picked a vector in one of our tangent spaces, an arbitrary vector just to compute this thing. As for U, it's the input to our stereographic projection. So if we have our sphere over here, I flattened it down for the sake of brevity, and we have our projection down to that point. This is U, and then it maps up to Xi tau on the sphere.
Where's the V now?
V is an element of the tangent space on TPRN. So have our tangent space here. V is going to be one of these vectors.
Wait, so P is the point U? Is that what you mean?
Oh dear, does it appear to have an inconsistency around here somewhere?
Yeah, P should be.
P should be
P should be U.
P should be probably be U and everything.
Yes. There we go. That makes things better. Okay, great. Thank you for addressing that. Are there any other comments or questions or concerns about this proof? Righteous. And now the last thing on the doc. Oh, sorry?
So you only did this G bar on two identical vectors. What about the different vector, V1, V2?
Sorry?
You only did it for V, right? So this is length. What about there's a V, two different vectors, V1 and V2? What's the...
So I will be transparent and say that this is a proof that's straight out of Lie, but my understanding is that just doing it with V with itself should be enough to compute what the metric is. Although the reason is not entirely clear to me at the moment why that is. Yes.
What if you apply this to V1 plus V2 in both entries?
Well, since we have a bilinear form, we can just go ahead and split that up outly. So you have like V1, V2, and the second one there. So it really only does depend, I guess, on which one we have, because any other vectors we can get just by adding them together. Is that?
Can you write that just so that?
Yeah, exactly. So let's say we had G of V1, V2 plus V2. And I don't know why there's this thing here.
Wait, there's more terms. There's still two more terms.
Sorry?
There's still two more terms. You got G of V1, V1. And then there's G of V2, V1, G of V1. It's bilinear.
Oh, yeah. It's been a minute since I've worked with them here.
Now, can you rearrange this to find G of V1, V2?
Yeah, you can do
I think so. Or I heard it called.
and then since these are symmetric, it doesn't care about the order that you put them in, then this is just going to be twice of whatever this is.
There you go.
And everything else is in terms of length. So.
Yeah, exactly. So.
Yep, you proved it on vectors that are the same in both entries. You're done.
Righteous. Thank you. Okay. See, that's all we only need to show that it. Yes. Okay. Now finally hyperbolic space. So the problem with hyperbolic space is that, by the way, I'll be using H and R for n-dimensional hyperbolic space, the radius R. Is that we have multiple different models we can choose from. You can either choose your upper sheet of your hyperboloid, or you can use the Poincare ball or Poincare half plane. Some of you may have seen these absurd shapes before. And the thing is, we have different metrics on these. So like for the hyperboloid, you can take the induced metric with the Minkowski metric, because hyperboloid sits inside Rn plus 1. And what the Minkowski metric is that it's basically almost the dot product. It's just that at the last term, you subtract that thing, the last coordinate, instead of adding it. While it's not clear that that's positive definite, it is, and we'll get to that later. Huh?
Oh, I'm sorry. You mean your pullback. Sorry.
Oh, yeah, sorry. My apologies.
The pullback is the Minkowski.
Yeah.
And then, whereas for the ball, and your half plane, you have these crazy things, which again, they look like the dot product, but with some added bells and whistles. As it turns out, though, despite the fact that we have 3 different spaces with 3 different metrics, they do all turn out to be isometric, which is awesome. For the purposes of time and simplicity, I'll only be showing that the hyperboloid model and the Poincare ball are isometric. The rest is left as an exercise to the viewer.
Are they isometric or conformally?
Isometric,
Oh, so
which
that
is awesome.
Okay.
They are actually the same, which is astounding. So, proof that they're isometric. Again, this is out of least. So again, some ingredients that we need for an isometry proof is first we need a diffeomorphism. And then we need a pullback metric. We got those 2 things, we're good to go. So first we need to find a diffeomorphism between the hyperboloid and the Poincare ball, and there does turn out to be a nice one, which we will refer to as hyperbolic stereographic projection. So you have your 2-sheeted hyperboloid here with stuck a disk in the gap there. And this is the one we're interested in, by the way. This is the one we use for our model. You pick your favorite point up here, and then you pick kind of like the vertex of your lower sheet, and you draw the straight line between them. And the point where that lands on the disk right there is going to be the projection point. This behaves very much in the same way that stereographic projection for the sphere works. You'll see more of that in a moment. It's kind of cool. And so a cloud of computations later, again, you can just do some equations of line stuff to show that these are some formulas that we can have to describe this map explicitly, where here pi denotes the hyperbolic stereographic projection. So now that we have that, and once again, this pi inverse here is going to be of particular interest. It does give us a local parameterization. We want to compute this pullback metric here. And as before, it's sufficient just to see what happens whenever we take the inner product of a vector with itself. So just a reminder, H1, this thing right here, is you take the induced metric with the Minkowski metric. And so we pick our favorite vector, and again, that should be u. I don't know why I keep doing this to myself. One day I'll learn to love myself and use notation that's consistent. This is the result of go ahead and taking the pullback metric there. Great. And now we need to figure out, again, what the heck are these things on the inside. So we step off to the side. And just a reminder, this is what the inverse map looks like. So we proceed as in the spherical case and compute these v, cj, and v tau. One thing you might notice is that it's basically just like the spherical case, just with all the pluses turned to minuses. And so you can really just think of the hyperbola as the sphere's evil twin. This is a common theme throughout the rest of this proof. And if you're a masochist, you can go ahead and compute these exactly to see that this is really what we get here. So all these put together, we have another crazy computation, which again, I'm not going to write out in great detail. But we get this thing here whenever the smoke clears. Now, does that look familiar? Let's go back up to, maybe I should like drag that so we have an easy reference. You're coming with me. Oh no.
Maybe it's a good idea to just copy it
Sometimes my Surface Pro doesn't like it when I copy things. I just know. So anyway, let's see. We have a 4. We have a 4. We have an R to the 4th. We have an R to the 4th. We have this thing in the denominator matching this thing in the denominator. This thing right here looks suspiciously like the dot product. So does this thing. And so that would tell us then that that computation right there isn't just, you know, some sort of thing multiplied by the metric here. It really is the same metric. So we have that these two are in fact the same metric, hence they are isometric. So here ends my grand extravaganza of Riemannian metrics. What questions, comments, concerns, or regrets do you have?
We just did what about the other example with the form?
The other one. My suggestion for how you proceed with that is you pick up Lee and go to chapter 3 towards the end. I was probably working on this at 1 a.m. last night, so I didn't get as many details as I would like to. Also, we are a bit over. Well, actually, no, we're at 50 minutes. We're doing good.
So if you check this complex half plane, that's just a component, it's much easier to see.
All right, it looks like we're all getting that. Or sorry, what?
Are there any other models people use?
I was actually looking at Wikipedia earlier, and there were other models. I unfortunately do not remember what they are off the top of my head, but there is a Wikipedia page that has a list of all these hyperbolic models you can choose from.
But so, I don't know, something we'll get to eventually.
Yes.
Is that, these are pretty much all your simply connected manifolds. Actually, it is all your simply connected manifolds of constant sectional curvature.
Let's see, let's write that down. So.
And that's kind of what makes them so special.
Of constant curvature, you said?
Sectional curvature?
Sectional.
That's going to be
And if
zero,
it's zero, it's Euclidean. If it's positive, it's a sphere.
Oh yeah, that kind of like that Gaussian interior curvature thing. Yeah, gotcha.
Yeah.
It's kind of reminds me of that number file video where they have like the bizarre way we eat pizza. I love Cliff. He's so funny.
That's sort of where
Okay, righteous. Well, thank you all for your time and constructive criticism. This has been awesome and a lot of awesome day. So.